Okay, so today's topic is graphs, and I kind of have like an intro slide to kind of describe things here. One of the things we do in physics is try to figure out what has happened, and maybe more importantly, what will happen. Really good science should always make a prediction. For example, I did this one, done this one before. If I let go of my keys, make a prediction as to what will happen. No, they did not. Okay. That's what good science should do, is should help you make a prediction. You say, well, they're going to fall, right? And one of the reasons why you know it's going to fall is based on experience, right? Experience would dictate that, well, every other time I let something go, it fell. In a way, you guys are on my 20-2 class for math, right? That's inductive logic, by the way. Or like, if it happened once and it happened again, and it happened a third time, and it happened a fourth time, eventually you start saying, well, it's probably going to happen the fifth, sixth, seventh, you know what I mean? Right? And if you can prove that deductively by actually coming up with the root causes for why something occurs, then that's really how like a law fits together. It's based first on observation, and then it's based on make a prediction, and then lastly you got to be able to explain, well, what the heck is happening, right? And when it comes to the keys falling, there's a theory that you probably heard about called gravity, right? And if we can explain how gravity works and make that logically fit with like the deductive reasoning, that's science, right? So the point I wanted to make here, though, is back to a graph. When you're looking at data, let's say that this is like a graph you've got going on here. Let's talk about the scenario and what's occurring here. This is a position time hand for a robotic arm during microsurgery. So you know how like a surgeon's cutting into a guy or something like that, right? Well, there are some things where they actually can use a robot to do surgery because the robot can make the just finest little incremental of movements that a person wouldn't be able to do, right? And like a person obviously still controls this from like a control room. So anyways, look at how this graph works. As it starts to move 0.2 millimeters, 0.4 millimeters, What's happening at the end here, though? Yeah, it's like it's not moving anymore, right? And so I have some words for that on the previous slide. Okay. One can interpolate is a word I'd like you to know. Interpolate basically means you use the graph and you read off of the graph currently being plotted. So if I were to ask you, where is the hand after 3 seconds? You look at the graph and you say, well, here's 3 seconds. You need to go after 3 seconds, it was right here. That's called interpolating, right? Where you use the data you currently have and you just kind of start with it. Does that make sense? But good science should allow you to go beyond that and start to extrapolate. Interpolate, extrapolate. Extrapolate is basically making a prediction about what's going to happen in the future. So does this graph go up to the 12-second mark? No, the graph stopped at 10 seconds. But I feel fairly comfortable in being able to say, I think I know what's going to happen at 12 seconds. Right, like if we put 12 seconds right here, based on the current pattern and rate of progression, it looks like it unless something changes, it's still flattened out and stopped. Does that make sense? So my goal today, basically, I actually have 2 goals. The first goal, though, with graphs is to help you guys be able to look at a graph and interpret what has happened and maybe even make a prediction about what will happen based on the current pattern. Now, there's one downside to this whole inductive logic thing, though. What happens if the guy who's controlling the arm all of a sudden slips and all of a sudden the thing just moves again, right? That could happen, right? But the idea behind this is to try to make a prediction based on at least the evidence we have. This is where things are going to go. You know what I'm So let's talk about some more graphs. So most of this is pictures here. There you go. Okay. So here's 2 typical graphs you guys are going to get on the test questions. Like I said, they're laid out for me. So all I really have to do is just show you how to answer them. So here's the 2 types. One's called a position versus time graph. One's a velocity versus time graph. And let's just try to figure out, based on what we know here, what we expect to have, what's happening. So what's happening right here at this point right there? Is the person moving yet? No, they haven't even moved yet, right? But then if it's position versus time, it looks like he walked a meter, and then the next second he walked a meter, and the next second he walked a meter. Right? This is a nice straight line. We have a word for it. When someone, is that one? Linear, that'll work, actually. From a math perspective, we call it linear, that's correct. From a physics perspective, we call it uniform motion. Do you remember that from our last notes? This would be considered uniform motion because he's always kind of walking the same speed, right? Like In 1 second, he walks 1 meter. In 2 seconds, he walks 2 meters. In 3 seconds, he walks 3 meters. So it's actually, you know how you call it linear? Linear things have a constant slope. If it has a constant slope, you are then going at constant speed. Therefore, you're going linear motion. So ideally, you'd be able to look at this graph here and tell me that, okay, this guy is walking at a steady pace. Now, that changes a little bit on a velocity time graph. Can you guys identify for me on the velocity time graph where he's undergoing uniform motion? Is it section 1, 2, or 3 where he's going at the same speed? On the second graph here, where is the van undergoing uniform motion? Girls. There's only 5 of you to teach it. Yeah, section 2 is where you're going to go uniform motion, right? Because what's happening here is he starts at 20 meters per second, and actually, what is he doing during section 1? Can you describe it? Yeah, the word for that is accelerating. He's accelerating during section 1. Then during section 2, he's now going the constant speed. And then what's happened during section 3? Deceleration. Until he gets to this point right here. What happens at this point right here? Good, he stopped. Yeah, exactly. Does that make sense? Like, you guys just need to be able to just look at a graph and interpret what's happening. So, the shape of the graph then kind of tells you stuff. If you were to have, say, a velocity time graph where the line was like right along the axis right here, in this example right here, he'd be literally not moving, right? Because there's no velocity whatsoever. You're just sitting in front of the firehouse, right? This graph right here, you're going at a constant speed because it's a velocity time graph, right? Because it's velocity and time, whatever that speed is, let's say this is 10 right here, he's always going 10. It's actually paddling in a kayak. Whereas here, this velocity time graph, here he's not moving at all, and he's getting faster and faster and faster and faster. So this last one would be accelerating. Next. Okay, so let's talk through this graph here then. What is happening during section A?
Deceleration.
Kind of. Why has the graph changed? Why is it not one of those L graphs? How did this all of a sudden become one of those T graphs? There you go, yeah. This is the guy backing out of the garage, maybe, right? Just looking at it there. Right? You got it right there, though, right? Here, he's going backwards. He's accelerating backwards. Then here, he's actually traveling backwards still, but he's not speeding up anymore. Then here, he speeds up even more going backwards. Right? Then here, he's still going backwards, but now he's going kind of at a constant speed. And then during this section right here, even though it's actually looks like it's one line, it's actually two sections here. You really got to consider this section right here. In this spot right here, he's still going backwards, but slowing down, yeah. At this moment right here, what happens? Yeah, he like, I don't know, pulls the handbrake, does a 180, turns around. Just for a brief moment in time, he's stopped. Does that make sense? And then now, he's accelerating forward. So, going backwards faster and faster, same speed going backwards. Speeding up in the backwards direction, same speed. Slowing down, but still going in reverse. Brief moment of stopping, pulls a brake, spins his car around Vin Diesel style in Fast and Furious. Right? Starts speeding up again, and then right here, then he's on cruise control. You guys feel like you could look at graphs like that and be able to interpret them?
Oh, yeah, sure.
Awesome. Okay, moving forward. Okay, this graph right here then is a little different. You guys remember how last year in math, we would have learned about quadratic graphs? This is kind of like half a quadratic graph, and how it has that like curvy sort of shape to it. Not all graphs have to be linear. Linear graphs usually mean that you're kind of doing something consistently, but this is a graph that's kind of a quadratic. What ends up happening on this graph here, see this is a position versus time graph again. So it's not velocity and time, it's position and time. Anyone want to hazard a guess as to what's happening in this scenario here? Okay, that's true. But is he going constant speed or not? No. Because if he was going at constant speed, it would be a nice straight line. So because it's kind of like curving like this, and he's getting faster and faster. Right? Like in 1 second, he went, say, 4 meters. And then in 2 seconds, he's now gone 10 meters. Well, he went from 1 and 4 to 2 and 10. That's a faster rate, right? And then in 3, he's now up to 20. That's even more, right? In 4, he's now up to, I don't know, 32, right? So the idea behind this one here, as you look at those points, is that you have a curved graph like this, it usually means that you're getting faster and faster. Okay, I know you're actually ahead of the curve in terms of what I was asking for here, but you hit on something that we need to know how to do. It's called slope, which we do slope in math, right? But the same sort of concept applies still when we're doing physics here. So one thing that you're going to be asked to do is calculate the slope of a graph. Before we kind of get to the rest of the notes, do you guys remember how to calculate the slope of a graph, what the formula is? Rise over run. Yeah, rise over run. It may even be in your formula book. Do you guys have that booklet? Yeah, don't break it. Do you guys still have that formula book that I gave you? I actually printed some color ones if you want to change it for a color. Sure. Yeah. Color ones. Everybody except for Buck. Okay, I'll use the old one here though. Oh yeah, there we go. It's on literally page 1. Can you guys see the turn to the inside cover here? Formulas and data. The very, very first thing it'll tell you is slope. Slope is rise over run. And it'll have like delta y over delta x, y2. You know what stuff like that? Okay, so let's just do a quick recap on this slide here about how to figure out a slope then. If you wanted to figure out the slope of, say, line A, you have to make yourself like a triangle out of it. Something like this. Like I would make a triangle like this and say that my rise looks like it's about 100. And then my run along the bottom looks like it's about 20. And then I divide those two numbers and find that the slope is 5. That makes sense? Okay. If I were to do the other graph, the blue one, blue's a little bit trickier because I have to start here. So on the blue graph, it looks like my rise is about 110 maybe. Along the bottom of my run is from 5 to 20. Does that make sense? Not from 0 to 20 because it doesn't start at 0. So 15. Right, and then whatever that is, that's your slope. Straight enough? Fair enough? So, anyways, the thing I need you guys to know then is when you calculate the slope means something. So if you want to highlight a couple of things here, if it's a position time graph, your slope is velocity. If it's position time graph, slope is velocity. And then I have this one down below here. But on the other type of graph that we're going to do in this section so far, if it's a velocity time graph, the slope is acceleration. So if you have position and time and you calculate the slope, it's how fast you're going. But if you have a velocity and time graph and you calculate your slope, it's actually how much speeding up you're doing. So, by the way, guys, if you want to write stuff in these books here, feel free to. So if you want to like write that in the margin somewhere for tests and stuff, I'm okay with that. Read the book. There's like so much stuff in there. Okay, one more thing you need to know how to do. It's called area under a curve. And while I'm highlighting stuff here, I might as well do a little more color here. We've never done this before in math, but I promise you, you guys will be able to figure out how this works. Do you want a second to write that? You guys will already. I'll pause. Okay, so here's the third one. This one's not about slope, it's about area under a curve is what we call it. A curve is just a fancy word for a line. Not all lines are necessarily straight lines, if that makes sense. So we just use the general term curve. So the idea though is that if you have a velocity time curve and you find its area, It's the displacement. So I'm going to show you how to do that in this example here. Let's say I asked you, according to this graph, how far you traveled in 8 seconds. Okay, I'm just going to make up a question. How far did you go in 8 seconds? It's a very typical question. You finished?
Yeah.
You guys gonna stick around the building or sorry, what was that?
No.
Alright, just make sure you sign the board then. Thanks, guys.
Bill, George.
Okay. So for this question right here, what you have to do is you have to make like a geometric shape out of this. So see how 8 seconds is right here? I'm just gonna draw a line straight up at the 8-second mark right here. And what it's gonna do is it's gonna create a box. You can see how there's kind of like a box that I'm kind of coloring in here. Okay. What's the area of a box? What's the formula for that? Yeah. So if the area of a box is length times width, we just need to know what those numbers are. So what is the length of this box? Or, well, I mean, just one or the other. I guess in terms of this side right here, it's 2.2. Does that make sense? I'm going to throw on a unit though. This side right here is 2.2 meters per second. How wide was our box across the bottom? Yeah, and by the way, the 8 seconds, I will have to tell you where you're stopping because I could have stopped here at 4 seconds. I could have stopped here at 10 seconds. So you do need to be told where to stop. But hopefully you agree that it was 8 seconds. Now watch this, look at the units here. If you have 2.2 meters per second, if I write it a little bit differently, and write it in like this kind of format here where I go meters over top of a second, if I write it like that, can you guys visualize how that seconds and that seconds will cancel? And I'll be left with, I think it's going to be 17.6 meters. Just grab a calculator and confirm that's what 2.2 by 8 is. Something 0.6. The key here, do you guys see how the units kind of cancel?
Yeah.
Right? And what we're left with is meters. So in 8 seconds, you traveled 17.6 meters. Right? So then if I were to ask you, well, how far you traveled in 10 seconds, well, then you'd change the size of your box. Okay. Now, boxes work really well if you have a really very flat line across. But I can't guarantee that every graph is going to be a flat line. So I might give you a question like this one here, where it's got some sloped lines as well. So let's try these 2 questions now. This is a very typical kind of 2-parter question. I give you a graph, and we've already looked at this graph before. Like, this isn't a new one. This is one we already used. Right here, speeding up. Right here, constant speed. Right here, slowing down to a stop. So my 2-parter question. First, let's find the deceleration of the band. Where is the deceleration of the band section? 1, 2, 3. Okay. How would you calculate an acceleration or a deceleration on a velocity time graph? Nope, not that. Look back at the notes you guys just wrote there, like because you wrote it in your books there. If you want to calculate an acceleration, what are we looking for? The slope of a velocity time graph. Because you guys probably wrote something like that down just a second ago in your books, right? What did you write? Velocity time graph slope is acceleration. Did you write something like that? Right. So we have a velocity time graph, right? If we want the acceleration, we need the slope right here. Okay. So let's make a triangle out of it. Here is a triangle out of it, but we're not doing, like you suggested, 1/2 base height. That's not what we're looking for though. That will find us something else. If we want the acceleration, we have to do our rise over run bit. So our rise goes from 30 down to nothing. Technically, we should make that -30 though, because you know how it's going like downhill slope. So the rise is -30, and then your run from 30 over to 45 would be 50. Watch the units here. The rise is in meters per second because that's the units of the up and down. So that's in meters per second. Your run is in seconds. So when you divide 30 by 15, you're going to get -2 because 30 over 15 is 2. And then the unit now is going to be meters per second squared. That's an acceleration value. So you're slowing down the 2 meters per second squared. That's how you calculate it. A lot of my kids, when I teach them this in their physics 20 class, they actually find this very frustrating because there's like no work to it, right? Like it's all just, do you understand how graphs work, right? Like the only thing you have to do is just divide two numbers. Does that make sense?
Yeah. Why is it?
Say that again? Because it's going like from start to finish, like it's going from 30 down to nothing. How do you get from 30 down to nothing? Well, you have to subtract 30 to get from 30 down to nothing. Does that make sense? So, lines that go like this have a negative slope. Lines that go like this have a positive slope. Alright, so there's the first one. So then for the second one, we want to find the distance traveled. If you want to find the distance traveled, the way you do that is you find the area under a velocity time graph. Okay, so the three things. If you want to find acceleration, it's the slope of velocity time. If you want to find velocity, it's the slope of position time. And if you want to find distance, it's the area under velocity time. So we got to find the area here. However, this one's a little more challenging. There's not actually necessarily just one shape. I would argue that we've got 4 shapes. See how I've kind of made 4 different shapes out of it? I've got a little triangle right here. I've got a rectangle here. I've got a square-ish looking thing here. And I've got another triangle there. So I need to find the area of all of those shapes. If I put all that area together, that'll tell me how far I've traveled. Does that make sense? So let's try it one more time. Triangle 1. The formula for a triangle is 1/2 base times height. Let's see, the base of this little bitty triangle looks like it's 5. And the height is 10. Makes sense? 5 by 10 is 50. Half of that should give you 25. And the unit, by the way, then would be meters. And the reason why is that this guy is in meters per second. And you're timesing by seconds. I already kind of showed you this. The seconds will cancel and be left with meters. So I don't need you to show me that. I just know that that's what it's going to do. So there's our first section. In this little bit right here, he's traveled 25 meters. But I have to account for the fact that there's also this box underneath it as well. So in box number 2, we just need like length times width, I guess. The length of the box, I don't care which one goes where, right? One was 5, the other one looks like it's 20. So 5 by 20 leaves you with 100.
Doing physics first.
With these guys, yeah. You guys okay with that so far? Okay, third one is also a length by width box. It looks like it's got a height of 30, right? So 30 is one of them. I know it ends up at 30 right here, but it's not 30. 25, you catch that. I don't know off the top of my head. 600 maybe? 750. Not even close. Oh, yeah, 30 by 20 would be 600. You guys still good with me? And then for the last one, 1/2 of base height is number 4. 1/2 of base height, so it's 1/2 of, what's that height again? Still 30? And the base is 15. I got 225. Any thoughts about what I should do with these four numbers I've calculated? That's it, yeah. Add them all up, yeah. Because that's how you find the area under a curve. So let's add them all up. 25 plus 100 plus 750 plus 205. I got 1100. Is that much?
Yeah.
Thank you. Oh, name. Oh, that's wrong. Okay. So, quick summary of what we've done so far then. I need you to know how to do three things using a graph. Okay. First one, if you want to find an acceleration, you need the slope of a velocity time graph. If you want to find velocity, you need the slope of a position time graph, or like distance time graph. And then finally, if you want to know how far you traveled, your distance, you need the shape area underneath a velocity time graph. So if you guys did, I mean, yes, you guys already wrote two of those down in your data book, right? So if you want to write the third one down, if you haven't, have you done that already? So the third one, you know how you already wrote down two of them from my previous slide? The third one then would be, if you want to calculate a distance, you need the area under a velocity time graph. That makes sense. So velocity time graphs are good for two things. They can get you the acceleration by the slope, or the distance traveled by the area. Whereas if you have the position time graph, the only thing it's good for is velocity. If you find the area under its graph, it doesn't mean anything. Sound good? Okay, so that's kind of the first part of the lesson, is trying to work with graphs. Okay. The second half of the graph, second half of the lesson kind of builds on it a little bit here. I just kind of have a new cover slide here. You know how we just finished calculating how far distance-wise you traveled? The one thing your textbook does a lot of is they want to relate this unit to the transportation industry. You can kind of see this even with the project that I'm giving you guys. The idea of collisions and vehicles and speeds and car crashes and stuff like that, right? So I found this picture right here. Here's a vehicle that, based on the skid marks it just provided there, looks like it had to stop on a dime, right? Like it's trying to come to a stop really quickly. And so if you want to figure out how far something has traveled, that's quite an important thing to do, right? One way you can do that then is using a graph. I'm going to show you a second way, which involves using some formulas. Okay, so I got some formulas on the next couple slides here. Before I get to that, there's basically four main variables we can work with. We can talk about distance or displacement, speed or velocity, acceleration and time. Those are kind of the main things we talk about. Guys, what's the difference between distance and displacement?
Displacement has it.
Yeah, like this one right here is a vector. Same thing with velocity, it has a direction, it's a vector. Does that make sense? So, the last thing I need to show you then is all the formulas we have. You guys have those booklets I just gave you. Can you flip to like the second maybe page inside there? It lists a whole bunch of them. We're going to be learning them, I guess, slowly over time here. So like the very first two we've already talked about. V equals D over T, V equals D over T, and then like A equals V over T. Skip down a couple. I don't know why they put them in this weird order, but for whatever reason they did. So skip over the F net one, over the F net one, over the W one, over the P one, and look at the two after that. You guys see there's a delta D equals VI delta T plus 1/2 8 of T squared. And the one below that is VI plus VF over 2. Those are the next two formulas I need to show you, where they don't involve new letters, right? Like they still involve the same combinations of distances, velocities, accelerations, times, right? It's just they're rearranged differently. Have we talked about the I and the F and what that means? Fantastic, good, okay. So my last little bit here is just to give you guys some practice, and this will probably be your least favorite part of this, but the good news is this is about as hard as it gets. We need to have good algebra skills to be able to use these formulas and rearrange for whatever we need to solve for. But I'm pretty confident you guys will be able to do this because it's a way lower level than what we even had to do in our like -2 class. So let's try some examples. Let's say that you've got a car traveling behind a slow vehicle, right? You've probably been here before. The guy in front of you is going 90. You're like, speed up. I mean, unless it's winter, and then maybe that's okay, right? So What do you do? Well, you pull over and you want to pass them. Right? That's logical. And I don't know, somehow your car measures that you're accelerating at this speed, right? Because you have to speed up to pass them, right? You can't just keep going 90 and expect to pass the guy. You're going to have to speed up, right? So you accelerate at this rate, and it takes you 5 seconds. My question here is, how far has the vehicle traveled? Right? And you can maybe imagine where this would be an important scenario. It's maybe not such a big deal in Southern Alberta where we have these double-lane highways, but I grew up in BC where we don't have any double-lane highways. And when you want to try to pass somebody, you have to pull into oncoming traffic sort of scenario, right? If there's a car coming towards you, you have to have good judgment skills to figure out, can I get around this guy before that head-on car crashes into me? You know what I'm saying there? Right? And so knowing how much distance you have, you might know, like, I've got to get around this guy by this point here, because if I don't get around this guy by that point, the car is going to cause a problem. You know what I'm saying? So, it's actually fairly easy, minus just the, you got to be good at algebra part. So, here's how I like to show my my physics 20 kids. So I'll do the same thing with you guys. I like to write out, right off the bat, the information I have. So let's start with the first one, that 90 kilometers an hour. What kind of variable is that? Like what letter would that represent? A, D, F, A, D, E, T. Is that a speed?
Yeah.
Okay. Is it an initial velocity or a final velocity? Is 90 kilometers going to be his initial and his final speed? Because he has to go faster than that, right? So he's starting at 90. That makes sense? That's his start speed. All right, then the next number we're given is this 0.50 meters per second squared number. Sorry, that wasn't overly nice one. What does that represent? Distance, time, velocity, acceleration? Good, yeah. Then it gives us a 5.0 seconds number. What does that represent? Time, yeah. And then for the last thing, usually you're given like a couple of different values here. There's always one thing that you're looking for. So I always just put I just put a question mark or a couple of them next to the last one. And the first thing we're going to look for is how far the vehicle has traveled. We'll make that one first. So if we're asking how far it's traveled, we're asking for, well, what is the distance? Okay? So I like to start here, just write out what sort of information we have that we're working with. The next thing you got to do then is go to your formula section and figure out which of these formulas here involves the variables you have. Like for example, I'm going to show you which one not to use. Don't use this one. And the reason why that one's no good to you is that you do know time. Time was a number we knew. And you do know velocity initial. But you don't know velocity final, and you don't know distance. You know what I'm saying here? And you can't have two things you don't know. So you have to pick a formula where you know everything except for one of them. And so hopefully you're kind of figuring this out here. The formula above it's really good for us to use because we do know the velocity initial, because that was 90. We do know time. We do know the acceleration. And this one just uses time a second time. Does that make sense? So let's write out that formula there. D equals VIT plus 1/2 AT squared. Do you guys ever do this in Science 10 actually? This is a formula that I gave you in Science 10 actually. You weren't in my Science 10 class, so. There's one issue though. And this is actually why there was a question on your assignment about this. We have to make a conversion. Your units have to be compatible. See how these right here are in meters per seconds, and this is in seconds, but this top one's in kilometers an hour? We can't have one be in meters per seconds and one's in kilometers an hour, because then the units won't cancel properly. So we have to make a good conversion, which is why that was a question on your assignment already. But you guys did this, right? 90 kilometers an hour. What should I do to get rid of, let's say, the kilometers? Where should the kilometers go, top or bottom? Okay, what should you put above? Meters. Because we want to get rid of kilometers. Oh, sorry. And then what's the ratio? Where does the 1,000 go? On the top or the bottom? Good, okay. Does that make sense to you guys? So now we have meters per hour. Then we want to get rid of hours. So put hours on top. You can go to seconds directly if you want. Do you guys know how many seconds are in an hour?
36.
That'll work, yeah. Or you can just do 2 sets of 60. I think I did this with a couple of you guys. We just did 62 different times. But if you want to, you can just say in 1 hour, there's 3,600 seconds. That works too. There's actually, I was looking through this book here. There's actually a sheet out there that tells you that sort of stuff. Just in case you don't know. Where was it? Second page?
Or the first page.
Yeah, there it is. Can you guys see like at the bottom there? It says some non-SI units used with SI. It's got like time there. So if you ever need to know those like equivalencies, there's some there. It's got minute to seconds, in case you don't know, right? Hours to seconds, days to seconds. Years, they use A for years. You ever heard that before? 3 years. So anyways, if you ever need to find that, you can just go right to that one. Anyways, I need you guys to help them. Can someone take 90 times by 1,000 divided by 3,600 for me? I'm fairly certain it's 25. Just because I have that one memorized. Just double check in case I screwed up. Yeah, that's 25. The reason I have it memorized is because when you do the conversion between meters per second and kilometers an hour, there's like one number that like, it's like even numbers on both sides. Like if you do 60, it gives you like 19.2 repeating or something like that. But like the one that has whole numbers, I just memorized it. 25 to 90. Anyways, we have what we need now to get started. So let's plug this in here. Your velocity initial is 25 meters per second. Your time is 5 seconds. Your acceleration was 0.50 meters per second squared. And then your time was 5, then you have to square that. Does that make sense? I'm just kind of plugging everything into the formula there. And all you just need to do is know how to put it in your calculator. So it'll look something like this. This one's quite nice because you don't have to do any algebra to kind of work backwards for anything. Oh, like it literally is ready to go as is. So you just got to do 25 times 5 plus 1/2 times 0.50 times 5 squared. Good. Now you know how much distance you need. You need 131.25 meters. That makes sense? Okay, there was a second part of the question here too. Sorry guys. The second part of the question here is how fast will you be traveling when you're done? So if it's okay, I'm just going to erase, so I have room here, but don't you erase stuff, I'm just going to erase it down below here. Okay. Now what I did is I took off the D, because D is what we were looking for last time, but rather than looking for D, now let's look for velocity final. You know what I'm saying? Right, because nothing's changed. You still started at 90 clicks an hour. You still accelerated at 0.5 meter per second squared. That got erased. Still takes you 5 seconds, but now you're looking for another variable. So what we need to do now is just figure out, well, which of those formulas is the one that's useful to us in this scenario. Does that make sense? So I'm going to go back then to the slide right here, and I need to find a formula then that has velocity final in it, but also has that other information. Which one might be useful? There's actually 2 choices. Actually, 2 different ways to do this. This one down here in the bottom corner. Because we know time, right? 5 seconds. We know velocity initial. And didn't we just find distance just a second ago? So even though I don't have it written down on my list right here, I kind of could write it in there because the distance was 131.25. Is that what it is? Alright. So the challenge though is, do you see how this VF sitting right here is not by itself? That's where your algebra skills come in. Okay. I'm not talking crazy like it was in Math 20 where you have to like do common denominators and factor and stuff like that. But you do need to know the right steps to solve. So let me write it up then. So the formula that we're picking was D equals, oh goodness, big bracket VF plus VI all over 2 times time. That's the formula. Okay. Most kids, when they do this, they prefer, but there's 2 ways. You could do all the rearranging now, or you can plug in your numbers that you have and then do rearranging. I prefer that myself. So I'm going to start plugging in some numbers, because I know some of them. Like, this D is 131.25. The velocity final is the thing that I don't know. Velocity initial was 25. And the time was 5. So all we have to do now is do our algebra to isolate for what VF is. So give me some thoughts. What's the first thing I should do? Actually, no, take it from this here. I have 3 numbers I have to remove to get VF by itself, correct? I have to get rid of the 2 off the bottom. I have to get rid of the plus 25, and I have to get rid of the 5. One of them has to be last. Which one has to be last? Not the 5. It's the plus 25. It's a binomial. Essentially, this VF plus 25 is a binomial. That kind of takes precedence. So I have to get rid of this 5 and that 2 kind of first. I would get rid of the 5 first myself. Like, I would divide both sides by 5. Like that. Now, I'm not actually going to type it in my calculator until I'm done, so that's just wasting time. Right, now see how there's like the 2 on the bottom here? To get rid of the 2, then I'll times both sides by 2. I'll get rid of that one. And then you see how now we've isolated the binomial by itself now? How do you get rid of the plus 25? Say that one? Yeah, subtract 25, yeah. So, I mean, my work is not exactly the prettiest right here, but can you guys follow how we're pulling this off? So, go to your calculator. In order to undo this, you have to take your 131.25. You have to times by 2. You have to divide by 5. And then when you're done, we need to subtract 25. All of that is equal to 27.5. That's meters per second, though, by the way. Which means that you were going 25 meters per second, and now by the time you're done, you're going 27.5 meters per second. So you're going faster, which you should be, right? Because you're passing the gap. That makes sense. That'll probably be one of the hardest things we do. If you can handle that, you're golden. It is something that we're definitely doing. I mean, not all these formulas that are in this data booklet are in the 20 course. So if you guys do end up taking Science 30, you know, like all these formulas in here, you will have to use them all at some point. But those are probably some of the hardest ones that are in there. Right? As long as you can handle that, you're pretty good. These are loud. All right, let's try another example. Diver steps off the edge of a platform, falls into the water 3 meters below. If the initial velocity of the diver was 0, how long does it take him to hit the water? Essentially, the idea is just like me dropping my keys. I'm going to drop my keys, and they're eventually going to hit the floor below. The question is, well, make a prediction. Remember that idea of where I started class, the idea of interpolate and extrapolate? Extrapolate should be able to mean, well, tell me what's going to happen in the future. My question for you is, when will it hit the ground? Make that prediction in the future. So let me do the same task I started with. I'm going to start writing out what I know. This 3 meters below, what is that a measure of? Is that like an A, a D, a V, or a T? 3 meters. Acceleration, velocity, distance, or time? Distance. Yeah, it's a distance. So the distance you're going to travel is 3 meters. It actually, that's the only number there. There's actually two that are hidden. One of them is right here. The initial velocity of the diver was 0. It's really sneaky, but there is a velocity initial of 0 meters per second. Because he's literally just stepping off the diving board. There's actually one more number that's implied. They kind of expect that you guys remember from grade 10. It's the acceleration. Do you guys remember what a gravity acceleration number is? 9.1. Yeah. Let's look for that in your data booklets, and if it's not in there, we need to write it in there. But I'm sure it's in there somewhere. It's got to be. Oh, there it is. It's in page 2 at the bottom. It's the under the astronomy data. It's the average acceleration due to gravity on the surface of the Earth equals 9.81 meters per second squared. You guys found that one there? So you'll be expected to just know that that's acceleration if things are falling. So the last thing we're looking for then is time. We need to calculate time. So we need to pick a formula that has all of these variables in it. I mean, obviously I'm picking the new formulas because those are the new ones for you. So this is the one you need. D equals VIT plus 1/2 AT squared. That's the new formula because it has all those, right? It has a distance, which we know is 3. It has a velocity initial, which we know is 0. We don't know time. That's okay. Well, there's one thing that we're allowed to have be the one we don't know yet. We know the acceleration, 9.81. And time, we still don't know it, but at least there's only one variable left. So I'll start throwing some numbers in them. This is going to be 3. This one's going to be 0 times t. And then this one is going to be 9.81, and that's going to be t squared. So far, so good? So we need to have our algebra skills. We need to get t by itself. In 20-2, you guys would have learned the quadratic formula. Now, we actually don't have to use the quadratic formula here, because I'm going to show you a nifty little trick as to why it won't be necessary. But you can see how it's kind of quadratic in a way, because you have x and x squared, only we have t and t squared. So the quadratic formula could be the way that you solve this. You just have to rearrange it, but this is really clever actually. See how there's a 0 times by t? Isn't 0 times by t just going to like make that nothing? Well, now I don't have multiple t's left over, I just have this guy right here. So to get rid of all the numbers surrounding it, I have to get rid of the 1/2. To get rid of the 1/2 times both sides by 2, I'll get rid of the 1/2. To get rid of the 9.81, divide both sides by 9.81. How do you make it so that it's no longer t squared? Square root, there you go. It's actually kind of good that we did math before science, just because you kind of use the skills from math in the science course, but like probably not to the same degree of difficulty. So we take 2, we times by 3, we divide by 9.81. And then if we square root the answer, there. Time is, let's call it 0.782 seconds. Is it go follow it? Okay, I think this is my last set. No, I got 2 more left. Okay. Sorry, this is kind of, these are going to be days where we're probably talking the most class. I'm sorry in advance. Back to like driving, because that's kind of where the textbook, like when you guys read through the textbook, that's what they seem to focus on all the time, is just cars that crash and stopping time. But a very thing that you might have to find is what's called a stopping distance, where as you approach the intersection right here, let's say that the lights turn in a different color, right? You got to figure out where is your point of no return. You guys have all been through driver something training, right, before. Like when you're about to go through an intersection, you've been taught. You know who taught this? That like you have to make a determination as to like where your cutoff point is, where it's like either you got to gun it at that point, or you got to start hitting the brakes. You got to make a choice, right? You can't just be in no man's land.
I just stop and
Just
I
stop in
get
the middle.
too scared. I just
Fucking stop. Alright, so the idea is basically what is your stopping distance? Like if you saw the yellow light when you were right here, could you still stop in time? If you could, you're supposed to start stopping, right? Whereas if you saw the yellow light right here, there is no way for you to stop in that short period of time. You may as well run the yellow, right? So I got two last examples here. First one here, it says that the reaction time for most drivers. The reaction time for most drivers is it's supposed to be about 1.5 seconds. So what that means is it takes you about 1.5 seconds to first have your brain process that there's actually something wrong, where you go, there's a car accident ahead, right? But then the other part of it is not only for your brain to process it, but for you to get your foot to the brake. Most people, it takes them about 1.5 seconds to get that far. Okay. So let's say the car is able to decelerate at this rate here. We want to figure out the stopping distance for a car traveling 125. So this is actually a two-part question. In part one, we need to figure out how far you go before you even hit the brakes. Does that make sense? Because you're going to be coasting along at $1.25 for a little while before you even get your foot to the brake. It takes you a while just to get to there. Does that make sense? That's part one. And then in part two, then you got to figure out how far you go while you slow down. Because you don't just instantly stop when you put your foot on the brake, right? It takes you a little while. So there's actually two different parts to this. How far you go before you even hit the brakes, and then how far you go while you're slowing down. We got to combine those two things together. Sound good? Okay, so let's list out what we know in the first section here. Before you even hit the brakes, there really is no, well, there's a time, right? The time that it's going to take you to hit the brakes is $1.50 seconds, right? We know that much. We also know your velocity, but this is a little bit different here. It's not a velocity final or a velocity initial, because it's just a straight up, you're going the same speed the whole time. So I'm not going to put a VF or a VI next to it. I'm just going to say that you're going 125 kilometers an hour as your velocity there. Right? I don't need to put an F or an I because you're going the same speed the whole time still. And then the last thing is we're going to find the distance that you traveled during that. Is there a formula that just involves D? Yeah, it's the V equals change in D over change in T formula. Okay, I got one problem though. $1.50 and 125 have incompatible units though, so we can't use two different unit types. Does that make sense? So we have to convert the 125 kilometers an hour. So, I mean, we did this a little while ago, right? 125 kilometers per hour multiplied by 1,000 meters in a kilometer multiplied by, in 1 hour, there are 3,600 seconds. That's what I got, 34.72. Okay. When you guys are doing your calculations, you should always use like the whole number if you can. So don't just round to 35 or 34. Like try to use the 34.72 number when we use that. Rounding leads to errors. Okay, so we actually have all we need to use that formula. We know the velocity is 34.72 repeating. We want to find the distance. We know the time is $1.50. I'll take off a second. Oh, maybe the units there. So algebra, how do you get distance by itself? Just times it up, yeah. So take that number times by 150. I got this, a distance of 5208 point. Oh, hang on, that's all right. I missed the 1.50. 1.50. 52.08. 3 repeating. There's a decimal sitting there. Does it follow that so far?
Is that 53 repeating?
Yeah, I like it's repeating. I just didn't write the bar. So based on what we have so far there, this is before you even get your foot to the brake, right? Like this is you driving along, la 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 la, cell phone out, hopefully not, right? And it takes you 1.5 seconds just to get your foot down. 50 meters has gone by, right? I mean, I don't know if you guys run track or stuff like that, right? But like that's half of a 100-meter dash. That's how far you're going to go before you even can start braking, right? This is one of the reasons why there's such big pushes to get kids to not be on their cell phones, right? Because 150 seconds is bad, but like let's say you're down like this, and 1 Mississippi, 2 Mississippi, oh crap, right? Like it's even worse if you're even slower than that because you're on your cell phone. So because now we have to get to the second part of it. Now you're actually going to start braking. How long will it take for you to start braking as well? So that was part 1. Now we need part 2. Okay, so let's talk in part 2. In part 2, we know your velocity initial because you know how fast you were originally traveling. You were traveling that 34.72 meters per second. We know that much, right? We also know the velocity final. It doesn't say so, but if you're going to eventually come to a stop, what's your eventual final velocity would be? 0, yeah. We need to know at least something else to make this work, because we want to know distance. But as I look at this right here, the other number we have here is the deceleration of 5.25. So I do have that deceleration number right there. Except I shouldn't use 5.25. I didn't make a negative. Why? Yeah, you slow it down, right? If you use positive 5.25, this would be you coming across an accident. You're like, oh no, there's an accident here. And you accidentally hit the gas. That's going to cause bigger problems, right? So we do need to be negative. Okay. Okay, I'm probably only out of time to finish this example. We'll have to read the last one until another day. Sorry. Do we have a formula that uses these 4 things here? VI, VF, A, and D. Look back on those 4 formulas. There actually isn't one that involves them all. So what we're going to have to do instead is first we're going to have to solve for time. And we're going to have to figure out how long it will take for us to brake. So we should be able to find a formula that uses VI, VF, A, and T, because that formula is this. Acceleration is equal to your change in velocity over your change in time. So my acceleration is negative 5.25 meters per second. Well, let's get rid of the units. I'll just use the numbers. On your formula sheet, that one with acceleration, does it do like VF minus VI? It does too. You see on the formula sheet it's VF minus VI?
Yeah, where is it?
Second page on your formula sheet. Third formula down? Fourth formula down?
Yeah.
Third one down. See how it goes VF minus VI? Yeah. Okay. So your velocity final is going to be 0. Your velocity initial is going to be 34.722 repeating. And we're looking for delta T. How do we get delta T by itself using our algebra skills here? You swing the delta T up to the other side, like you times this one up here, but then you take the minus 525 number and you bring it back down and it's close. So delta T is going to be, okay, 0 minus 34.72. Isn't that just going to be minus 34.72 repeating? Divided by minus 5.25. Here's why that minus is so important. two minuses divided by each other makes a, which is good because time should be positive.
When the 5.25 become a positive?
You're dividing it though, not adding it. You're dividing it. So make minus 34.72222 repeating divided by minus 5.25, and I've got a time value of 6.6137 or so seconds. Yeah. So based on the conditions that we were at least given here, not only is it going to take you a second and a half to just start seeing the accident, but if your car can actually decelerate at this rate, it's still going to take you 6 seconds to stop the car. The question is, how far are we going to travel during that time? So here's our last step. There's a lot to do. Now let's use the formula D equals VIT plus 1/2 AT squared. We use that formula. Because I want to know the distance, right? But I know my initial velocity. I was originally traveling 34.72 repeating. I know how long it's going to take me because time I just found a second ago was 6.6137, something like that. Here's the really important one. You know when you use this acceleration right here though? Use the negative number. So I'm going to make that minus 5.25. And then I have to do time another time, so 6.6137 squared.
Whoa.
Yeah. This is probably the hardest of what we end up doing. It's where you're using like multiple ones of these formulas. So let's try this. 34.72 repeating times by 6.6137 plus 1/2 negative 5.25 6.6137 squared. It's going to take you another 115 meters to slow down.
You're not going to drive
Well, this is why people usually end up rear-ending other vehicles, right? Now, I'm not saying, like, let's say that you, like, when you add these together, right, you've got, this is 114.8. The other number was 52, let's call it. Right, so when we add those two numbers together, you end up needing about 167 meters. Okay. Now, this is why a lot of cars will get into at least some sort of accident, a fender bender. Because let's say that you don't have 167 meters to stop, you only have 150 meters to stop. Yeah, you're going to hit the guy in front of you, but you're not necessarily going to smoke into him. It just means you're going to hit him with like 5 to 10 kilometers an hour. You know what I'm saying there? As you're slowing down. So, which still causes whiplash, right? The guy who gets hit in front of you still causes a problem, right? So this would be the safe distance you'd require to have no accident whatsoever.
Wow.
Okay, I'll leave the last question for now because it's going to be a lot anyways. Quick summary of our data. There's really two parts to it. Part A, can you look at a graph? Can you figure out the three things off of a graph? Can you find the slope for either acceleration and velocity or the area for distance? That's the first one. The second one's probably the harder one. Can you use the 4 formulas on your formula sheet to solve a question? And sometimes you have to use multiple formulas to solve questions. Like sometimes it'll just be one step and it'll be easy, but you need to know how to use all 4 of them.
That sounds hard. It's easy to do, honestly. I'll get
Okay,
it.
last thought here, and then you guys can probably take off. Let me just look back at the assignment again now and talk about what you can solve. Okay, so here's the assignment now. Hold off on this one here involving force. You can come in, we're not quite done yet. Hold off on 9 and 10 involving forces, but you guys should now be able to do like this number 11 one involving graphs and looking at them. And all of the ones on the back page are pretty much what we just talked about, where there's a car driving and then it needs to react and then it needs to eventually brake. And so you can do some of these questions here. You might even be able to do all of them except for this one involving Newton's laws, which we're getting to next week. Okay. Final thought. This may not be enough practice on its own. You guys should really try a couple of the questions in like the textbook. If you want, I'll find you some. But you probably can't do well at this and just walk into it cold. So if you want more practice than this, let me know. I'll find you some in that textbook. Okay.
Sounds good.
Okay, we're done. Okay, so I just said a minute ago that ultimately my goal of these 2 lessons in sequence here is to teach you how to factor things that are cubic, quartic, and quintic. The requirements of me is to prep you all the way up to 5, but honestly, you should be able to factor 6s and 7s. It's just, at that point it gets ridiculous, because it's not harder work, it's just more work, and it's just frustrating, right? Like, yesterday I think I gave you guys a question where you had to like, do something to the power of 3 to cube it out, and like, you're foiling this, and then you foil that, and you foil this into that one, right? And it's not probably hard, it's just there's a lot to it. So that's my goal over the next few days, is to build up to that point. And I want to use our previous section as a bit of a launching point to get there. So what I want you to do is consider the 4 main ways that we add equations or variables or numbers together: add, subtract, multiply, and divide, right? As I've got on the slide here, the first 3 are actually pretty easy, right? If we were to add these ones together, you guys should be able to handle this. 3x plus 2x will give you 5x. 3 minus 1 will give you 2. There you go. Right? That was pretty straightforward, right? Subtracting, you just got to be careful of like double negatives and stuff like that. Like 2x right here has nobody to subtract to, so it's still 2x squared. Minus 4x minus is another x to give you 3x. No, hang on. Made my mistake right after I told you not to do that. Make it minus 5x. And minus 4 is subtracting 7 more from minus 11. Okay. And then on the multiply one, now you're really foiling, so you're going to get 3x squared plus 9x minus 7x minus 21, or 3x squared plus 2x minus 21. And so this point here that I want to pause. Actually, I'm going to close the door so I don't hear loud yell. Really good shit, isn't it? You guys get up to that point there, though? Okay. What did we do when we multiplied? What's like the word that we used to describe that process? Or like the acronym. You know what I'm going for here? FOIL, yeah. Right? Essentially, multiplying was foiling, right? Now, if the opposite of multiplying is dividing, what's the opposite of foiling? Factoring. Well, expanding is not a word for foiling. Can I say that again now?
Yeah.
So, what we just did on the slide right here, we expanded, right? Which, or foil is a good word to use, right? So multiply associates with foiling, right? Now, we've never really described this before, but if the opposite of multiply is divide, then is it the opposite of foiling to factor? Aren't those kind of reverse processes? Now, many things, no, I shouldn't say this, everything is easy to foil, right? You just go this by this, this by this. But is everything possible to be factored? And the answer to that is no, not everything actually is factorable, which is why last year we spent a good amount of time working on the quadratic formula, because for things that can't be factored, that's kind of your backup method. Right? So what I want to focus on now here is, let's talk more about that division concept and how we can use division to help us with our factoring, because those are going to be some skills hopefully you can recognize that it'll be useful. Right? So if polynomials can be divided, I think I spelled that one wrong there. It may not be easy to tell. So let's talk a bit first about what division means then, because I find that when I teach this, kids have forgotten how to divide. They have a calculator, and the calculator literally, you just type it in and it does it for you. So we should really start at like ground zero again here, and mind you, like grade 4, when a teacher taught you how to do division, what does division mean? Okay. You guys remember doing long division at all?
Yeah.
So long ago? Okay, let me walk you through what long division really did here. You'd start with 32. And you try to figure out, can 32 go into 4? In a way, when I say the words go into, it's like if you were to have 32 people, could you divide up 4 cookies amongst them? Well, no. if there's 32 people and there's 4 cookies, are you each getting a cookie? And the answer would be no, there's nowhere near enough, right? So what ends up happening right here is we put a 0 up top there, signifying that of these 4 cookies, we cannot split them up amongst 32 people. Right? So then, in terms of like how this thing works, then we move on to the next column, and we combine them together, and we would then say, well, maybe not 4, but how about 48? If we had 48 cookies and 32 people, could everybody have a cookie? And then now the answer is yes, everybody could get 1 cookie. Right? Now, are there going to be leftovers? Yes, there's actually a remainder, hence the title of today's concept, the remainder theorem. What we then did here is you take 1, and I'm going to skip down to this step here. You do 1 times by 32 to get you 32 right here. Then what happened right here is they subtracted. And they did 48 minus 32 to get 16. And we have a name for this. We call this the remainder. Which hopefully that kind of makes sense, right? If you had 48 cookies, 32 people, everybody gets a cookie, but there's leftovers, right? Now, if we want to keep this process going, maybe you remember this idea of like dragging down like the next digit, like you drag down the 7. And now we have the number 167. You then say, well, if you have 167 cookies and 32 people, how many could you make work, right? And then you kind of reverse engineer it in your head and say, well, let's try 5. So you go 5 times 32. 5 times 2 would give you 10, carry the 1. 5 times 3 would give you 15. Add the 1 to it, make it 16. That's why there's a 160 down here. That makes sense. This 5 kind of multiplied by this right here to give you the 160. You then subtracted, and it gave you a remainder of 7. Now, your calculator though doesn't give you that as an answer, right? Because what your calculator does, and this is why I think it's worth to remind you of this process, even briefly, is that if you were to take your calculator and do 487 divided by 32, it gives you a decimal number. But sometimes in real life, if you have, like, say, the number of cookies, I can't maybe cut the cookie in half. So what ends up happening is, sure, there's 15, everybody gets 15 cookies, but there's 7 leftovers. In a way, you see this remaining decimal number right here? If you took 0.21875 and turned that into a fraction, there's 7 30-seconds left over, which is 7 out of 32 left over. And that decimal is the remainder. I promise you, at one point in your life you knew this. But we didn't need it anymore because at some point you just move past that, you just use your calculator, and we just move on. We just do that one more time to make sure you get the concept. When you do this long division stuff, right, we'll re-go through the process about how this works, right? But by the time you're done, sometimes what we do is we have a remainder, how many leftovers there are because it doesn't divide even, right? If you have 8 and you divide by 2, fantastic, it's 4, right? Easy. But what happens if I have 19 and I ask you to divide by 7? Can you divide 19 by 7? Well, I mean, sure, I did it right there, right? But put in a real world scenario, you have 19 cookies and 7 people, you're each getting 2, right? Well, you get 2.7, but if you can't break a cookie up into 0.7, right? So if you think about this for a second here, 19 divided by 7 means you each get 2. Now, reverse engineer this a bit. 7 times 2 should be 14, right? But there were 19. So what's your remainder? 5. Make sense? Well, now look at what I just did here. If I do, I hope this works, 0.714285714. That's a repeating number. I'm going to keep doing that. 714285714285714. I'm going to try this. Try to turn it into a fraction. Yes, it worked. What does this mean? Well, it means there was a remainder of 5 out of the original 7 left over. See how that works? So those principles, we're going to have to use those to some degree when we do the exact same thing though, but not just with numbers, not just with letters. I'm going to show you how to do this with entire equations, because we're going to try to divide entire equations from each other. So it may be easiest just to bear with me. Trust me, okay? I will not let you flail away like this for forever, but I'm just going to do the first example. Okay? Watch, soak up as much as you can, then I'm going to erase it and do it again, and I'm going to try to fill in some of the gaps, okay? So, for the first time here, don't even write, just watch, okay? Okay, trust the process. I'm going to show you how to divide long division lines. It looks like this. I'm going to take x minus 2, and I'm going to divide it into 5x to the 3 minus 13x squared plus 10x minus 9. So it kind of looks like the division statement that you did back here in the same sort of way. What's going to happen is my answer is going to be left up here if it divides. It may not actually divide evenly. There might be a remainder left over, which is fine because lots of things have remainders left over. It's just for most of our lives, we either do one of two things. We either ignore remainders or we turn the remainders into decimal numbers. We do one of those two things. So let me try this. First thing you're going to do, I'll even color code it for now, is we're going to ask ourselves, well, how many times can x minus 2 go into 5x cubed? And the answer to that is 5x squared. This is one that blows people away, so just be patient, okay? Here's how I'm going to prove that. When I ask you how something goes into something, that's asking you to divide it, right? If you have 5x to the 3, and you divide out an x, well, if you divide out one of your x's, you're left with x squared, right? But you still have a 5 left over. So, but I'm not going to put the 5x squared in this column right here, because wouldn't it make sense to put the 5x squares in the column that all the other x squareds are kind of in? So the next thing we did in long division is we take this and we multiply. We go like 5x squared times x gives you 5x to the 3. But then we take 5x squared and we also times it by the minus 2 because it's a binomial. And it gives you minus 10x squared. That looks somewhat similar right here to like when we took the 1 and times by the 3 to get that 3 right here. But we also took the 1 and times by the 2 to get that 2 right there. Then we put a line down here and we subtract it. Same concept. I'm going to put a line right here and I'm going to subtract. 5x to the 3 minus 5x to the 3 is gone. It should, because I've now divided it out. But there's a remainder left over. This remainder is going to be negative 3x squared. Because negative 13 subtract negative 10, double subtract means add. So you actually have negative 3x squared left over. And that's kind of like what we did right here, where you got this 16 left over. We then dropped down the next term, which was a 7. So I'm going to drop down the next term, which is a 10x. Repeat the process. How many times can an x minus 2 go into a minus 3x squared plus 10x? Focus on the first term. How many times can an x go into a minus 3x squared? Maybe think of it rather than multiplying, think of it as dividing. If you take minus 3x squared and you divide out a single x, you'll be left with minus 3x, not x squared, just x. So I'm going to put a minus 3x in this column along with all the other x's. Kind of like back here, these are all of your 1s, your 10s, your 100s. You got to kind of keep them lined up. Same concept. So then I do this kind of multiply concept. Minus 3x times by x does give me minus 3x squared. Minus 3x times by minus 2 gives me plus 6x. I'm now going to subtract. In the process of subtracting, minus 3x minus minus 3x just goes away like it should. 10 minus 6 gives me 4x. Again, drop down the next term, the 9. Wait, how many times will x go into 4x? This one's actually the easiest one of all to think. The answer is 4. Right? If x were 2 times by 4, it would be 4x. So I'm going to put a 4 right here. In the same way, how many times can 32 go into 48? Once. Hence the 1 right here. How many times can 32 go into 167? 5. So x minus 2 is going to have to times by that 4. So that's going to give you 4x minus 8. Then I'm going to subtract. And when I subtract, these guys cancel. And I'm actually left with minus 1 left over here. I'm now out of terms. Now, when you do long division, what they typically do is you put a decimal place and you start pulling down zeros. And that's how you start getting like the decimals that kind of show up afterwards. But that's not really appropriate in this scenario here because this is your cubics, your quadratics, your linears, your constant terms. We're kind of out of digits right here. So what we have left over here is this is known as a remainder. Long story short, does this divide evenly? No, it does not. All right. Now, if it divides evenly, let's talk back to where I started class. Okay. Remember how this was factoring? Factoring is what happens when you multiply. Well, the opposite of factoring, no, hang on, that's not right. We didn't factor there. We foiled. Foiling is what happens when you multiply. Well, then dividing is going to be factoring. Is everything possible to be factored? Well, no, we even learned that with like our quadratic stuff. Not everything can be factored. If I ask you to factor x squared plus x plus 100, that's not factorable because I'm never going to find a number that adds to give 1 and multiplies to give 100. Like it's not always possible, right? Well, what I've just shown you now is that in this particular example right here, this thing right here, I now know what one of its factors is not. X minus 2 is not a factor. That's what I proved. So what I'm going to slowly but surely show you then is how to use this to first figure out what its factors are not, but then to eventually figure out what its factors are. Does that make sense here? So this sort of long division thing here, we're going to get there, I promise. It's just going to take us 2 days. So, wait, let me pause there. That makes sense, kind of the first go around? Okay, let's try to get as a group now. So I'll erase it, and we'll try it again here. Let's see if we can help you through the process. Jessica, Michael, and Brooke. This is similar to when I showed you guys synthetic division real fast the other day. I'm going to show you synthetic division again in a second, actually. So there are some correlations to what we did that one day. All right, so let's try this again. This time, follow along with me. So we're looking to do long division. We want to figure out, ultimately, here's our question. If it divides, it's a factor. Does that make sense? All right. If it does not divide, then it's not a factor. So what we're really doing is we're narrowing down whether or not this thing might be a factor. So let's try the process. The first question is, how many times can you fit an x minus 2 into a 5x cubed? Just focus on the first terms. Well, this x right here, if you have 5x cubed and you divide it out into x, you'd be left with 5x squared. That makes sense? That's kind of the division that you're doing there. So, erasing that because that's going to get in my way. I need a 5x squared to go right here. 5x squared. Now, using that same sort of long division process, this is not going to factor evenly at this point, because if I re-times this back together to kind of check my work, 5x times x will give me 5x cubed when I re-times it by this here. But it also needs to get times by the 2 to give you minus 10x squared. Did this section right here divide evenly? No, it didn't. It left me with a remainder. The first little bit canceled out, right? When I subtract this stuff here, that stuff canceled out. But when you do minus 13 minus 10, there was a remainder of minus 3x squared left over. So as of this point right here, there's a bit of a remainder left over. Good news though, we're not out of numbers, right? There's another digit left. So let's pull down the next digit. I'm going to use new colors to kind of help keep track of things. So the next question, can x minus 2 divide from the minus 3x squared plus 10x? It's not going to divide evenly, but I mean, I can try dividing out at least the first term. If I divide this x right here by the 3x squared, it'll give me just minus 3x. So I'm pulling one x off of it. Well, then I try to figure out how much excess there was left over by redistributing this. If I do minus 3x times x, I get that minus 3x squared, which I should have. That was the whole point. But for the next term, when I do the minus 3 times the minus 2, I get plus 6x. Did it divide perfectly? No, it did not. Especially when I subtract. The first terms will go away, but for the next one I'm going to get 4x. So again, there's a remainder bit happening right here. Didn't fit perfectly. But again, I still have one more term I can use. I can pull down the minus 9. This is probably the one that you guys can see best here. Think of this here. Is x minus 2 going to fit into 4x minus 9? No. What would it need to be for this guy to fit inside that one? Not the 4x minus 9, but 4x minus 8. You guys see that? What I'm saying there? If it was 4x minus 8, this would have been flawless. This would be like when you divide two numbers by each other, and by random luck, it just hits even. You know what I'm saying? Like if I were to go to my calculator, and I were just to pick, you know, this divided by that. If it happened to be on an even number, wonderful, right? But what are the chances of that? Right? Well, I mean, with polynomials, hopefully they can be factored, right? If I did 78 times 98, all right, so if I did 7, 6, 4, 4, divide by 78, once in a while, it will just be on a whole number, right? But in this particular example right here, we can actually visibly see, hopefully, that now the x minus 2 isn't going to go into this bit here. I'll do my best. I'll try timesing it by a 4. Right? If I put a 4 here, 4 times x will give me 4x. If I do 4 times minus 2, it'll give me minus 8. When I do that last little subtraction, there's a minus 1 left over. It didn't quite factor evenly. Okay. Now, for our ultimate goal of factoring, sometimes finding out what it's not is actually still helpful. Okay? This is where, when you start learning how to factor cubics and quartics and quintics, sometimes it's not necessarily harder work, it's just you have to do a lot of it. Sometimes you have to narrow down what it isn't before you find what it is. Let me show you what we've now accomplished, though. If I were to take that x minus 2 that I had right here, if I were to FOIL it, you know how the opposite of divide is multiply, right? The opposite of factor would be to FOIL. If I were to FOIL it by this 5x squared minus 4x minus 4, watch what happens. 5x squared minus 3x plus 4. Yeah. Let me just watch this. That'll give you 5x cubed. That'll give you minus 3x squared. That'll give you plus 4x. That'll give you minus 10x squared plus 6x minus 8. When I put it together, see how when I redistributed it, I got that? That is almost what I have right there. Almost, though. This is minus 9. This is minus 8. The reason why is we have a remainder. You know how when we divide, there's that decimal number that's left over? This is kind of like your decimal number that's left over. If I were to subtract one more, which was my remainder, then I would have what was right there. That's like your leftover bit. That make more sense? That's the second time. It's something you're going to want to practice. Okay? It's not something you have to do all the time, because this is actually one skill along the way to a larger concept, that concept being learning how to factor. So we don't always have to do this, but you should definitely try this once in a while. So, okay, here's kind of another way of approaching it. This is back to kind of the cookies concept. I was using that before. See here I have 7 cookies, and I'm going to divide them amongst 2 people. So if I divide 7 cookies amongst 2 people, they each get 3, but there is a remainder left over. In a way, I can kind of write that with polynomial statements here. If I have a polynomial and I divide it by the binomial, which, by the way, in terms of what that means, p of x would be this guy right here. This guy here would have been the p of x. If I were to divide it by this quotient, this guy right here, it produced this guy right here. We call that the quotient. You guys know that term, quotient? So this was your polynomial. I divided my polynomial by that quotient, or by this binomial here. It gives me a quotient. So if I do this and divide by this, it gives me a quotient. But there was a remainder. But the remainder is like a fraction. Remember how, like, when I was doing this example back here, just with numbers, if I did 9 divided by 7, it gave me 1 point, let's pick a better number, 9 divided by 5, 1.8. Okay. So think about this with cookies again. You have 9 cookies, 5 friends, they each get 1 cookie. Right? How many are left over? 4. Right? 9 cookies, 5 friends, everybody gets 1, and there's 4 left over. Does this answer right here show you 4 in it? Well, okay, no, this answer here doesn't show you 4, but if you break it up into 1 plus 0.8, think of this as being the 1 right here. Think of this as being the 0.8. Okay. Isn't 0.8 4 out of 5? There is your 4 right there. See how that kind of pieces together? Okay, let's try another example. You guys ready to try one on your own, or should I do this alone? Brave? Try it? Try it on your own. Take a few minutes, try it on your own. I will catch up to you in a bit, okay? See whether you can replicate the same steps I did. See whether it divides. If you're absolutely stumped as to where to start, I'll give you that. It looks like this. X minus 1 goes into x to the 4 minus 2x to the 3 plus x squared minus 3x plus 3. That's kind of like your setup. So you guys can see how, when I'm talking so far about how we kind of start with numbers in like elementary school, and then we do like algebra in junior high, and now we're like doing this with equations. This is probably one of the toughest things we do all year, actually, because most kids start with long division on their own, just with numbers, let alone like saying, let's do this with equations. That really ramps up the complexity. So yeah. So there should be a subtract. minus x over 3 minus another minus x over 3 gives you 0. But then we do x squared minus x squared, that should give you 0 right there. Yeah. Which means you have to pull down this number. I should pull down the next number too. Pull down 2 numbers in a row. And then we'll that way. Yeah. Here, I'll start catching up to you this time. Okay. If you're really stumped here, start looking at the board here. I won't maybe talk so much here. I'll just start writing some stuff, and you guys can compare yours to mine, and then I'll talk about it afterwards. So I'll start catching up to you here. Okay, so Jamie, you got to this spot right here where they both cancel? Yeah. Okay, so when you get to the next step here then, you know how you're supposed to pull down the next number here? Pull down both of the next numbers and go directly to the step here. And then, you know what's going to happen here is when you find this next number here, it's going to end up being minus 3. You're going to put that in this category right here because you don't need any x's basically. So check yours against mine. I agree, but in order to get this one right here, you go minus 2x over 3 minus x over 3, which gives you minus x over 3, not plus x over 3. So that you have minus 2, you're adding that 1, which means minus. And what that does is it makes this minus, which means you're going to have a minus there. Good, which is the point I'm going to make to everybody else in a second, but it actually means that these do evenly divide. Right? Say if I were to, pull out random numbers. Okay, those didn't evenly divide. Those were the remainder left over, right? But, I mean, 46 and 2 divided by 92. This one I designed on purpose. Evenly divided, there is no remainder left over. Which means that these guys right here, they are the factors. This is one factor, and that is the other factor. So we've now found a way to start factoring our cubic term. Yes, exactly. That's exactly the concept here. Is by dividing, multiplying, spoiling, dividing is our way to factor. It sucks because it's hard. There's no 2 Well, no, there's 0 x. Did you have the same one? Yeah. So basically, we can say that this times by that should equal this. So that's our first way of factoring. Is we know that this is one factor and that's a factor.
See this one? The one that made it?
So I don't know whether some of you guys are at the point where I've got to the screen here, but see how there is no remainder left over? This means that they actually are factors. They will divide evenly. So you could say this then. This is equal to x minus 1 and x to the 3 minus x squared minus 3. This thing does have factors, and here are those 2 factors. If you were to, I'm not going to suggest you do, but if you were to refoil all this mess, it should equal that bit right there. Does that make sense? So this is our way of kind of starting the process of figuring out what the factors happen to be. You guys managed to get that?
I got that.
Just the last one.
No, where the x is cancelled.
Okay, so now that you've gotten down to this step right here, see the minus 3 with the x right there? Let's put a minus 3 up top. But let's put it in the 1 just column. Yeah. Okay, so now go minus 3 times x, which is minus 3x right below that.
how many x go into there?
Minus 3 times 1 minus 1 gives you plus 3. So subtract those, gives you 0.
So it makes it.
So this did divide evenly, so you can now say that that whole quartic can really be broken up into 2 factors. This is one of the factors, that's the other factor. Okay, but right here it can't be this one. This is minus 3, minus 1, even positive 3. Okay, so here's what we hopefully can break from this concept here. If you write it like this is a way by trial and error of figuring out what your factors might be. Here's the problem though. I just told you that x minus 1 was the number that you divided by. How are you going to know whether you use x minus 1 or x minus 2 or x minus 3 or x plus 1 or x plus 2? So although this helps us figure out, first of all, whether or not it is or isn't a factor, it's actually kind of trial and error. So what I need to show you guys over the next little while, and maybe let's take a quick break because I still got more to do. So I'm going to show you a shorter way of doing this. It's actually the same sort of stuff, but it usually speeds things up a little bit. And then I'm going to get to the point where I show you how to figure out what to actually divide by, because this guy right here, how will we know which one to attempt to divide by? Does that make sense? So we'll take a quick break though, because I'm probably talking to you till 3:30. So we'll take a quick water break or walk around the school. Okay. Before I show you the next section here, I was thinking in my mind as you guys are on break here about how sometimes in math, and this is no fault of your guys, but the way we teach it is we show you how to do something, and then eventually we show you faster ways of doing it. Because, I mean, that long division method I just showed you, it's actually quite tedious. It takes a while. And so there's been a method developed called synthetic division, which speeds things up. And really, you're actually doing the same thing. What we do is we eliminate some of like the little steps just to try to streamline the process, if that makes sense. So I want to show you that, but I also want to guard against the idea of don't just completely forget this and be like, oh, well, I'll just use the shortcut every time. Because for 2 reasons. Okay. First reason is when you do this in math in general, as soon as you start taking the shortcut method every single time, you start to forget things and like your brain atrophies. As an example, right off the bat, when I showed you guys the whole long division concept, you probably knew this at some point, but let's say I gave you the 9 divided by 4 concept. It's 2 1/4, right? But another way of writing it is 2 with the remainder of 1, right? And the reason why is that if you take 0.25, the leftover decimal number, turn it into a fraction, it's 2 1/4, right? Everybody, if there's 9 cookies and there's 4 of you, everybody gets 2, and then there's 1 more that need to get divided amongst the 4 of you, and since you can't do that, then there's just 1 left over, or if you can do it, then you each get 0.25 of the cookie, right? You probably knew that, but at some point, especially you guys are taking my physics class, when I ask you to do 8.25 divided by 9 times 10 to the minus 87, we stop thinking about that, right? And we don't think about it being like 9 and 0.16 as a remainder, right? Like that just, we forget about it. You know what I'm saying there? So the first thing I want to point out is please don't forget about how to do the long division stuff, because that is fundamentally like what math is based on, right? Even when I give you a shortcut, you should still try to remember what we're actually doing. But there's actually a second reason that matters more to you guys. You're probably going to get some diploma exam. Now, they don't do written response anymore, but what I've seen them do a lot of is they show you somebody's work, and they ask you in somebody's work, find the mistake. And so a really common question is they show you somebody trying to do long division, and then somewhere in their work, they've made an error, and it's your job to try to say, well, they made an error on step 3. Does that make sense what I'm saying there? So when I show you this next section here, please don't just be like, oh, I'm always going to synthetic division, because I promise you, you're going to want to. This is so much faster. But really, you're doing the same thing, just we're speeding it up. So let me show you how this works then. Take this one back here where we used to have all these variables in here. Okay? As a way of speeding it up, synthetic division basically means let's get rid of all the stuff that I don't need. And so I'm going to do a whole bunch of erasing here. Okay? But before I do that, I need to fill in a few more things here. See how this x3 right here? There actually is a coefficient in front of it. Oh, so that's a 1. And there's a 1 here, and a 1 here, and a 1 here, and a 1 here, and a 1 here. See how there's like 1s everywhere there? What synthetic division does is it says everything else is just kind of lined up though, isn't it? These are all the x cubes, all the x squares. So let's just stop writing in all this extra stuff. Because by writing in all this extra stuff, even this x right here, we can possibly get rid of. Let's get rid of all of this. If we were to do this, it sure would make it a lot faster because you're not writing all those extra little details. Does that make sense? So it's actually going to look very similar, and we're actually going to do the exact same question, I believe. We're going to use, oh, no, this is a different one. Okay, well, we'll do this one here, and I'm going to show you how synthetic division works. So first, pretend you're setting it up using long division. Like, set it up using sort of the same sort of concept. X plus 3 goes into, but here's how I change it a little bit. This is my design for it. Everyone does it a little bit differently. I make kind of a grid out of it, and I'm going to throw a 2, oh, hang on, we're doing it above. I'm going to throw a 2 up top. That 2 represents the 2 from the x to the cube. Then I'm going to throw a 3 next, which just represents the 3 from the x squared. A minus 4 after that, and a plus 15. You see how I'm kind of like streamlining it, so I'm not writing all of the coefficients out? It's just to save me some time. Here's how synthetic division works. Treat it as sort of a grid. Okay. You can make it a full-on grid. I don't usually draw it like this. I think I showed you guys something slightly different. So here's the first step. Okay. You know how you're supposed to drag down in long division? You kind of drag down your next number. You know how that's kind of the thing that we normally do? Well, you're kind of doing that here. Only before we start, this is actually the first thing we're doing. We're going to drag down our first number. I'm going to drag down the 2 into the first location. That's the first step. You're dragging down your first number. It's kind of out of order, but it's similar steps. Well, then you take your coefficient right here and you multiply it. What is 3 times 2? 6. Okay. Well, we kind of do that sort of stuff right here. When we were doing this work right here, once you had a number that went right here, you'd take this and you'd multiply it there and put it in a new location. So you're kind of doing the same thing, but in a different format. I'm going to take this 3 times by that 2 and get you 6. And it's going to go right here. That's the location it goes. This 3 times that 2 to get you 6. Well, similar to the long division, you know, at some point you kind of put a line here and you subtracted stuff. Well, I'm doing the same sort of thing. I'm going to subtract some values from each other. Those values, though, are right here. This 3 is going to subtract that 6 right there to give you minus 3. This 3 subtracts that 6 to give you minus 3. And then you kind of repeat the same process. You're going to go 3 times by the next number down here, minus 3. 3 times by minus 3 will give you minus 9. It will then take this location right here. Then you take the 2 numbers that you have right here and we're going to subtract them from each other. Minus 4 minus minus 9 really means to add. So you're actually adding it and making it 5. Last step. Take the 3 times by the 5 to make it 15. Then subtract. 15 minus 15 gives you 0. Now, this honestly is the exact same type of math you were doing in long division, because what do you do in long division? In long division, you were finding a number, you were multiplying it, writing it down here, and then subtracting it. Right? Like, it's the same type of calculations you're doing, only I erased all of the x to the 3's, the x squareds, and the x's. Now that we're done, let's put them back in. This guy right here of 0, if there's a 0 left over, did these things divide evenly? Yeah. This is your remainder. This 5 right here then is your constant term, so don't put anything next to it. This 3 right here is how many x's you have. And this 2 right here is how many x squareds you have. So if I were to ask you what happens when you divide them, did it factor? Yeah, it did, because you got a remainder of 0. It factors to this, x plus 3 and 2x squared minus 3x plus 5. If you wanted to, you could add on your remainder with a remainder of 0. But like, we never write on a remainder if it actually divides, right? Because that'd be silly. Right? But if there was a remainder, you might like add 1 to the end of it. To just do a quick cursory check here. If you FOIL this, isn't that bit right there going to give you 2x to the 3? Well, we need a 2x to the 3, right? Isn't this 3 times that 5 going to give you a 15? That makes sense. I mean, I don't need to maybe do all of them, because that's going to take some while, but what we've now proven is that we can actually find out what the two factors are using synthetic division, and it's so much faster. Okay. What I need you guys to know is that, 1, you should know the basics of what you're doing here and how that works, and 2, it's on your diploma anyways. So don't completely ignore this in the future. But I'm going to bet you that like 9 times out of 10, you guys are going to want to try it this way. Let's do another example. On the blank slide right here, why don't we try the one that was on the slide 2 before that one, which was, what was it? It was like x to the 4, help me out here, minus 2x3 plus 3. And then what were we dividing it by? X minus 1. So let's try this using synthetic division again. And I promise you, you're gonna find this to be much faster of the two methods. I just want you to know what is happening, because sometimes I think we teach kids how to do something in math. They don't remember why they're doing it. They just do it, you know, because they learn the rules. So here's how this would look with synthetic division. Minus 1 is kind of what needs to go in this kind of column right here. And then the coefficients, because we're going to skip all the x's and all the x squareds. The coefficients go up here. So we need a 1, a minus 2, a 1, a minus 3, and a 3. Those are our coefficients up there. The long and short of it is we're always multiplying and then subtracting, which isn't that exactly what you do when you do your long division? You put a number up top, then you multiply it, and then you subtract it. You get a new number, you multiply, subtract, right? So, but the key for the first one here is that really there's like a 0 in this column right here. So in a way, when you do 1 minus 0, you kind of drop down the 1. That's kind of where you have to start. So often I don't write a 0 here, I just kind of drop down the 1 and then we begin. So, let me know if I lose you guys. Minus 1 times 1 gives you minus 1. Minus 2 subtract minus 1 really means to add. So minus 2 going back up 1 gives you minus 1. Minus 1 times by minus 1 gives you 1. 1 minus 1 gives you 0. Minus 1 times by 0 gives you 0. Minus 3 subtract nothing remains at minus 3. And then minus 1 times by minus 3 gives you 3. As soon as these two numbers line up, you know you're doing it right, because 3 minus 3 gives you 0. Which, now working backwards, this is then your remainder. That is your constant term. This is how many x's you would require. This is how many x squareds you would require. This is how many x cubes you would require. Take a look at this. Is that not the exact same thing we did up there? But it's streamlined. It's a lot more efficient. Does it follow that? So what's the key to this then? If something's going to be a factor, what is the remainder going to have to be? 0, right? Say that out louder. If something's going to be a factor, the remainder better be 0. Because if there's a remainder, then it didn't divide nicely. If it doesn't divide nicely, then it's not a factor. Does that make sense? So that's the key. If this is 0, we're golden. Which leads me to my next concept here. I want to do two things that seem unrelated, but then I want to show you how they fit here. Let's take this function right here, and let's plug in f of -3. I know this seems like I was driving this way, and I'm going somewhere else, but I promise these two thoughts are actually very closely related. I should have enough time to do them both. I'll probably have to run out of time. But this notation, what does it mean to do? This is what we did like the last couple of days. If I have f bracket -3, it means to make all the x's -3. So watch this. 2 -3 cubed plus 3 -3 squared minus 4 -3 plus 15. Two seemingly unrelated things. I just flipped the long division stuff back to where we did the last couple of days. When I'm done with this, this is going to give me an answer, correct? Like a numerical number, right? As opposed to those non-numerical numbers. Okay, so let's find out what this is. 2 bracket -3 in brackets cubed plus 3 bracket -3 squared minus 4 bracket -3 plus 15. Equal to 0. Okay, I want you to see the relationship between these two things though. This function right here was this function that we did a little while ago. And I know it's two examples, but do you see how this guy right here, the 2, 3 minus 4, 15, is the exact same one that I did right here, the 2, 3 minus 4, 15? But I want to talk about terminology for a second here. Here I tried to divide by x plus 3. X plus 3 is a factor. Does that make sense? What is the root of x plus 3 as a factor? Minus 3. Someone really brilliant once came along and discovered, hang on a sec, if I want to figure out whether something is a factor, here's how I do that. I plug in a root, because you know how roots and factors are the opposites of each other. If I plug in the root and it equals 0, then it's a factor. So again, if you plug in a root into the formula directly itself and it equals 0, then it must be a factor. Because think about that. Here's a graph. You know where -3 would be like over here? If -3 does give you 0, doesn't that mean that it's right along the axis? So if -3 gives 0 like it did, then x plus 3 is a factor. And this is where we're going to have to pick things up a little bit tomorrow then, is the idea of we don't have to flail away in the dark and just guess about random things. We can actually speed up the process drastically by trying what's called the remainder theorem. And the remainder theorem basically says if you want to figure out what something is a factor, plug in a possible root. And if the root works, we now know what a factor might be. Which is what I have on this slide right here. If you want to figure out the remainder theorem basically states that if you plug in the a value of your binomial, so if you plug in the root for the factor, that'll actually tell you what your remainder is. Okay. Look at this example that I found on the internet here. Here someone has actually gone through and done the long division for you. Okay? They found that the remainder is 2. So based on that knowledge, is x minus 3 a factor of this stuff right here? No, it's not. Okay. But I could have done that way faster by doing the remainder theorem. If this right here is a possible factor, what is the root of that factor? Plus 3. Watch this. If I do 2, 3 squared, minus 5, 3 minus 1. I'm taking this guy and I'm flipping it around to this one. That's 9 times 2 is 18. Minus 15 makes it 3. Minus 1 makes it 2. I did that in all of like, what, 10 seconds? I don't need to do the long division because I already know it's not going to work. Where am I going here? And so we only have to do long division on things where we know that it's going to work anyways. So that's the remainder theorem. So let's try an example here. Let's figure out whether when we divide these, it's going to be considered polynomial or rational when we're done. First, we should talk about what that means. If it's a polynomial function, will it divide? Yes. Okay. If I try to divide these two things by each other, if it's polynomial, yes, it will divide nicely. If it's a rational function, it won't divide nicely. Does that make sense in terms of terminology? So really my question here is, let's see whether this will divide. Now, I could do this. I could go x minus 3, try to put it into 11x minus 4x squared minus 7. I could do that. That's a waste of time. If this is my factor, what's my root? 3. So let's go 11 times 3 minus 4 times 3 to the 4 minus 7. And let's see if it equals 0. If it does, it's a factor, and these things will divide, it'll stay polynomial. If not, then it's not. And then it's considered to be rational, which is our next unit anyways. So that's 33 minus, I'm fairly certain it's not going to be 0 right off the bat here, because that's 33. That's like 81 times 4, which is like really big. And then you minus 7 more. I don't think it's 0, right? So based on this, I now know that this is going to be a rational function because these two things do not divide by each other nicely. There is a remainder. Makes sense? Oh wait, do I have enough time for the last one? I think I have just enough time here. So here's what we're going to do. We're going to try to apply all of those skills now that we've learned to try to solve this question here. Is this not on yours? How did that get in there though? Okay, well, let me just make one up then real quick. Bear with me for a second. I got a book here. I'll just make one up to finish the class.
Please excuse interruption. Can the following students please come to the office for messages? Mackenzie Hearn, Aurora Chiefbody. Please come to the office for messages.
Okay, so just so you guys know, I'm in the book here. I'm looking in the graphing polynomials function. I'm going to do graphing polynomials. I'm going to do number 12, which looks like this: minus 2x to the 3 plus 4x squared minus 3x plus 1. That's the one right there. Okay. And I'm just going to try to figure out what a factor might be of it. So I'm just going to try a number. Let's try, and let's just see if it divides by x minus 2. And I just picked x minus 2 randomly. There was no rhyme or reason for that. Two options. You can do long division or synthetic division. It would look like this. You take your minus 2, kind of plug it into your graph like this. You'd get minus 2, 4, minus 3, 1. And I did some synthetic division. I did it really fast. Okay, but if you guys look at my synthetic division right here, will this divide based on what I see in the synthetic division? And based on this last number here not being 0, no, it is not. So I know this guy right here is not a factor by doing synthetic division. That makes sense?
I think, yeah, I think that minus 2.
It's minus 2. Oh, it should be 0. Good call. It probably still doesn't work though, does it? Let's do a reverse on this. Minus 2 times 0 is 0, minus 2 minus 0 is minus 3. That makes it a 6. Minus
Kenny Wells and Skylar Frank, please
That makes
come to
sense
the
so far?
office.
So that's what I spent most of the time showing, is how to do this process. But the fast version of it is to say, well, option 2, if x minus 2 is the factor, let's test the root if the root does in fact equal 0, then it was a factor in the first place. So I'm going to take the same equation I just had there, which was minus 2, but I'm going to put in plus 2. So here I'm plugging in the opposite, which is 2. That'll give you 8 minus 16. That'll give you plus 8 minus 6 plus 1. That'll give you minus 6 minus 12. Ooh, did I do this wrong? Do this wrong. 4. 2 times 2 times 2 times 2. That's minus 16. Oh, that's 16 right there. There we go. Alright, that was minus 5. Okay. This is the remainder theorem. So long as you don't screw up on basic math. You see how I got a minus 5 right here? I got a minus 5 right here. Either way, the answer to tomorrow's question about whether this is a factor, we know it's not a factor, but I've proved it quickly by determining that there is a remainder. The remainder is minus 5. These two things do not divide evenly. So, last thought here. You guys can start packing up while I talk, though. Tomorrow our goal then, you guys okay? Sorry, I'm almost done. Tomorrow our goal then is to help you guys not flail away in the dark. And you know how I just randomly said x minus 2? We're going to have to now try to figure out what numbers to actually use. Should we use minus 1 or minus 4 or minus 3? So that's our goal tomorrow. And then we're going to start factoring full on cubics and quartics and quintics. So most of tomorrow is going to be factoring the x to the 3, factoring the x to the 3. Does that make sense? Okay, I'll pause it there. We'll pick this up again tomorrow. Thanks for bearing with me for a long lesson, guys.